Yeah, and that's when I was like,
Wanker, mate.
oh, for fuck's sake, not this fucker again.
Boy, mate, malware checkpoint, ain't it? You know the drill, mate.
It's okay, just act natural. Remember everything that I've taught you. Just go on. Go on, give it to the bastard.
What's your problem, huh? I cannot believe you gave that asshole this. I mean, have I literally taught you nothing?
What is your obsession with being mediocre? You're telling me, for all the impossibilities it took for you to be here, breathing this air, the sum of all of these insurmountable impossibilities led to this hippo shit? Oh, I never did teach you, huh? Well, how about we fix that then, you... dramatic fiberglass laminator? As is the case with pretty much everything on my janky ass channel, this video contains information that, if used negligently or maliciously, can get you in serious trouble. This is just for educational purposes. In the previous video, I talked about why we'd even want to make malware, since I know a lot of newcomers are raising their eyebrows at the notion of making malware. I'm not going to reiterate all those points here, but you have officially been warned not to use what you learn here today maliciously or against something that you don't have the explicit written permission to do so. Seriously, I don't want to see any of your head asses in prison, especially you slouching in your little chair. Anyways, disclaimer done. Back to the video. Oh man, that old dickhead really gave you the works, huh? You know, that reminds me, you wanna know how you can get back at him? Or how to make some shit that won't get caught by any fucker in a light reflective vest? Come here. You can start by checking out the sponsor of this video. Maldev Academy is a great friend of the channel and a great fit for what we're all about here. Listen, pal. You want to make some real malware, and the Academy wants to teach you how to do exactly that. What could be a better trade than that? What's that? You don't think you're ready? Idiot. It's called an academy for a reason. Maldev Academy will take you from the absolute basics, like learning the basics of C programming and Windows internals, to encrypting your payloads and techniques for hiding and spoofing your malware and making it harder for defenders and analysts to examine your malware, all the way up to some crazy shit like bringing your own vulnerable driver, DLL sideloading, event tracing, hardware breakpoints, and so much more. Seriously, just an assload of stuff here, and all of it's just Through text-based learning modules that linearly progress in difficulty, you'll make your way from a snotty loser that gets stopped at every checkpoint to a... There are videos to watch as well with some lessons, and you get access to a super slick virtual machine already sorted with all the source code from the modules and all the required tools you need in order to develop and test your malware without the headache of doing a Windows install. Oh my god. There are constant updates, and every month since the Academy has come out, they've been pushing out incredible stuff for the lifetime members with so much planned for the future. That list is only growing. Okay, well, you might be thinking, how about something practical to do after learning something from one of those juicy modules? Did you do all your work? Including the objectives? That's right, homie. Lessons come with objectives for you to do as well. And what's that? You want something more than that? Say no more. There are dedicated challenges for you to do that will really put what you've learned to the test. Upon joining, you also get an invite to an awesome Discord server, which is a refuge to literal one-man apps and fresh newbies like me alike. I mean, just look at all of these incredible people and still not convinced, huh? Well, what if I told you that using my special code, CROW10 at checkout, you'll save 10% off your order? Yeah, sounds like a bargain, doesn't it? Well, a huge thank you to Maldev Academy for sponsoring this video and continuing to provide amazing content to us. If this sounds good to you, use the first link in the description or look at the pinned comment to get 10% off your order at checkout. I'ma see you sweethearts in Kernel-mode. A little bit of a recap. It's been a while since we last did some actual process injection, so let's revisit the code from the last video. Oh, this? I'm just trying to protect myself from whatever radioactive gunk I used to think was acceptable back then, you know, in the context of coding and shit. You might want to step back. This is gonna be what the fuck? First of all, second of all, thankfully, I like to think that I got a little teensy-weensy bit better since this disastrous and traumatic time in my life. So let me reformat this code into how I program this out now, and then we can talk about this and what it does. here's how I do shellcode injection right now without focusing on evasion at all. Alright, so the first thing that we see is I'm not setting up any of my variables outside in the global scope. That's just going to come back to bite us in the ass later when it comes to debugging and stuff like that. You know, when you make a function, typically you want to keep all those variables inside that function. It also helps other developers know what's exactly going to get altered. You could initialize it with 0. I'm just keeping it null for completeness sake, but I mean, you could just do that if you want. I have my shellcode here, and it's going to be placed in the read-only data section of our file because of this const keyword. Now const makes it so that this won't get altered, hence why it's going to be placed in .r data. Don't worry if you don't know what this means, just a little thing to keep in your mind. There's different payload placement areas where you can place these payloads. I also want to get you guys in the habit of considering that, because you can place it in .data, .r data, .resource. There's a bunch of different things like that. But the rest of it is pretty much the exact same. I just have it formatted a bit differently. I tend to use this formatting thing a lot that I really like. And there's this cleanup label. So there is a bit of a debate when it comes to programming in general, actually, to using go-to statements in your code. Now, generally, it is a frowned upon thing. People don't like when you do go-to. First of all, the main gripe has to do with readability. I find that for simple cleanup like this, you know, if we do need to like exit the program and close handles, this is perfectly okay. I myself love doing this. I know a couple of people that I know like using labels, and it's just a matter of preference. This is really nifty. With that done, this is it. It's very standard stuff. Let's take this shit for a spin. So as you probably know by now, all this technique does is allocate a region of memory into your target's process address space with whatever permissions you give it. At the bare minimum, to be able to execute your payload or your shellcode, you would have to give this allocated buffer read execute permissions. In the previous video, we gave it full read write execute permissions, which is a really big red flag for defensive solutions to see this unbacked omega powerful page being allocated to a process. But I did mention how using virtual protect, you could start with a buffer that's allocated with read write and then change it later on to read execute when you're actually ready to execute your payload. And although this is better than just doing a straight up RWX buffer from the get-go, we're still fighting an uphill Sisyphean battle if we choose to stay in the realm of Win32 API. We have to go deeper. You see, Win32 API, as incredible as it is bloated as fuck. Like your mom. The general rule when it comes to things like evasion is that the lower you go, the better off you are in terms of stealth and control. You see, the lower you go, the more difficult it is for the defenses to surface shoulder, and the lower you go, the more fine-tunability you have. Win32 is like the exact opposite. It's the highest level of abstraction there is when it comes to programming using Windows API as a whole. Because of this, virtually every function has been documented and blasted to high Hrothgar with the fucking graybeards. That's one of the reasons why that checkpoint guy caught you so easily. Fuck you, guy.
Wait, mate. Wanker, f you, wanker, mate, wanker.
So what do we do then? Win32 API is out of the question. So what do we do? Are we doomed? I mean, who will save us from this torment? As we touched upon in previous videos, most of the functions that we've used in our programs was exported by a library called kernel32.dll. This library houses a shit ton of the Windows API functions we know, love, and have previously used. Now, you'd be forgiven in thinking that if you were to call a function exported from kernel32, that it would execute immediately. But unfortunately, that's not the case. I mean, it's more complicated, but chances are, if you're even watching this video, you're already into that kind of stuff. Maybe, hopefully, even wishing for it. Freak. Don't worry, so am I. From here, we can see that virtually everybody familiar with NT has, at the minimum, heard that there is a hidden API that NT uses internally. This API, which is called the native API, is almost entirely hidden from view with only a handful of its functions documented and generally accessible publications. This obfuscation has led to a general belief that the native API can provide applications magical powers, perhaps even allowing them to bypass security measures implemented by standard APIs like Win32. Thoughts along these lines usually led to the native API conspiracy theory that Microsoft is keeping the API for themselves and their own applications to an unfair advantage. You know, I am getting ahead of myself here. There's something that we actually have to discuss before we even talk about NT API. We know that it's a native API, but what the f does that even mean? And more importantly, what does the native API do for us and for the functions that we call? Now, it's very important that we spend some ample time and effort understanding the next section, because you're gonna hear it all the time and it's, you know, kind of important. We're gonna be talking about user mode and kernel mode. So we're gonna differentiate between these and exactly where everything is and what happens. In your malware development journey, you're gonna be hearing user mode and kernel mode. You probably even heard me say it a couple of times in my other shitty ass videos. I don't even know why you guys watch. So it's not without reason, okay? A lot of things like anti-cheats, antiviruses, EDRs and stuff, they run in kernel mode. They do this because running in kernel mode gives you access to all the parts of the operating system, which if you're detecting and defending against malware, it's a really important advantage to have. Now, there are things out there like malware that also exist in the kernel space. I know a lot of people currently working on kernel boot kits and stuff like that, and it's very fascinating. To protect user applications from accessing and or modifying critical OS data, Windows uses two processor access modes, even if the processor on which Windows is running supports more than two: user mode and kernel mode. User application code runs in user mode, whereas OS code, such as system services and device drivers, run in kernel mode. Kernel mode refers to a mode of execution in a processor that grants access to all system memory and all CPU instructions. Some processors differentiate between such modes by using the term code privilege level or ring level, while others use terms such as supervisor mode and application mode. Regardless of what it's called, by providing the operating system kernel with a higher privilege level than user mode applications have, the processor provides necessary foundations for the OS designers to ensure that a misbehaving application can't disrupt the stability of a system as a whole. And this is the importance of these protection rings. Back in the day, you could have your entire computer sitting on the most privileged ring, kernel mode, but that would mean if one say you're playing RuneScape and it crashes, your entire computer is just gone now. That's why these core protection rings have been introduced, and that's why on processors nowadays there are 4 privilege levels or rings to protect the system code and data from being overwritten by accident or on purpose, by code of lesser privilege. And these rings help facilitate what's called the principle of least privilege. From the world's most scholarly resource, we can see that in information security, comp sci and blah blah blah, the principle of least privilege, also known as the principle of minimal privilege, POMP, requires that in a particular abstraction layer of a computing environment, every module, such as user, program, depending on the subject, blah blah blah, must be able to access only the information and resources that are necessary for its legitimate purpose. TLDR, you as someone in ring 3, you cannot access the lower level rings, not directly. If you want to use a function, you're not going to be able to just go into the kernel and do that. You got to use Win32 API, which is going to translate down into the native API, which will then go into the kernel, because you are not allowed to touch the kernel. So if we look at this following image that you might find all over the place, you can see that there's these rings, right? Let's go through these rings. Ring 3, this is where we are. If you start an application, this is where it's going to be. Things like your web browser, text editors, games, fucking potassium permanganate sniffing simulator 2018, whatever it's called. This will run in user mode, and user mode has the lowest level of permissions. It allows like things for you to do gaming, browsing, editing, all that shit without crashing the entire operating system with it, right? It's very important that these privileged rings are separated. And ring 1 and 2 are typically used by device drivers, but you might not see them used a lot. They are a mostly privileged level. And ring 0, obviously the kernel. This is where the kernel is. It has the highest permissions, it has access to everything, can communicate directly with the hardware, and if something breaks here, it could crash the entire system. Now, the reason why Windows only uses 2 levels is that some hardware architectures like ARM today, MIPS, and Alpha in the past only implemented 2 privilege levels. Now we have covered kernel mode and user mode, and it's a pretty high level, but it'll be enough for us to understand what's happening. You can see this is very fitting for the spooky month. Yeah, the NTAPI is this sort of ghosty hidden presence in our computers, operating in the background, in the shadows with the OSU players and the freaks of nature. This is making everything work under the covers, and it's been around for a really long time too. The native API is exported by a library called ntdll.dll or ntdll. And this library is ultimately the final stop that most of our functions end up in after being called from kernel 32 before reaching the threshold into the kernel space. But more on this in a minute. The NTAPI has its own syntax as well. Typically, function names exported from ntdll have 2 to 3 letters prefixed before the functions, which also denote what they are, what they do, or what group they belong to. NT or ZW is the most common ones you will see as you program, but there are other notable ones like LDR or RTL or debug or whatever. You will see these from time to time. When you call a function like write file or create process or whatever, we already know that these functions are exported by a library called kernel 32. We also know that these functions eventually end up in NTDLL, where they will then reach into the kernel using certain instructions. These instructions are either going to be a syscall instruction, the hex2e interrupt, or the sysenter instruction. We won't delve too much into this right now because that'll be covered when we talk about direct and indirect syscalls in a future video. But the point is, we call a function from kernel 32 and it ends up in NTDLL. However, I would be doing you a disservice if I didn't point out that there's a little bit more to this, and it's not just step 1 kernel 32, step 2 NTDLL. No, there's a teensy bit more to this. To demonstrate what I mean, let's take a look at this horrifying graph that I made. Hold on, what the hell is this block? Why is there just this random ass library kernel base that houses the same function name as the one from kernel 32? Well, if we look from the bastards themselves, we can see that this library was actually talked about before. And if we read the description of this page, we can see why this was done. To improve internal engineering efficiencies and improve foundations for future work, they've relocated some of the functionalities to the new low-level binaries. This is just done so that it's easier to provide subsets of functionality to reduce surface areas, which include disk and memory requirements, servicing, and attack surfaces. And from the manifestation of impact, we really see what happens within kernel base. As an example functionality that we move to low-level binaries, kernel-base.dll gets functionality from kernel 32 and ADVAPI 32. This means that the existing binary now forwards calls down to the binary rather than handling them directly. So we see that kernel base, sort of, in the highest sense of the word, kind of acts like a proxy. I mean, you're forwarding your calls down to it. A lot of you guys probably use Burp Suite too, so you're probably familiar with this whole proxying thing. It's not exactly a one-to-one, but you can think of it like that if it helps. Shit, I mean, enough talk. How about we actually dissect a program and see this for ourselves, huh? Here, I've just strung together a little stupid-ass program that just gets a handle on a process and then closes that handle. All these WinAPI functions like open, process, and close handle shouldn't be new to you by now. And if it is, just go back and watch the other videos. I'm getting butterflies. This is my favorite part. So you can do this in so many different ways. There's not a shortage of programs and applications that let you see things in a more magnified view, you know, a software microscope as I like to call it. Things like debuggers or tools made specifically for API monitoring, whatever it may be, just pick one and stick with it. Although I'll also say that it can be very, very insightful to do the same procedure using multiple different tools, just to catch the differences in nuances and syntax and stuff like that. Like you could take this program and throw it into WinDebug, and after doing that, you can throw it into x64 debug and then into IDA and stuff like that. Okay, this is attempt number 2. I don't, for some reason, my audio capturing software completely fucking bugged out and I lost the last 20 minutes of work. It's taking everything inside of me to not leave a head-shaped hole in my desk. So let's just see if we can do this again real quick, okay? We've already talked about this, we know what this does. If we try to run it, just make sure everything's working. It expects a PID, so let me just try to open a terminal, and then I already have a notepad open right here, so let me I'm just gonna use some PowerShell scripting because I cannot be bothered. All this does is gets a process name, we filter for the name of a notepad, and then we output all that out because it's going to be too much information if we don't filter it. So then we redirect that into select and expand property, just makes it so that we only get the ID. Effectively what this is just doing is just getting the number value. So if we press enter, we should see that we get a handle. Perfect, we get a handle, then we press enter to exit. There we go. So we know this works. Let's open it in one of my favorite debuggers, x64 debug. So what I'll do is we find our application and just open it. So the first thing we have to do before we even do anything is go up here, change command line. We have to find the process ID of that notepad. Let me just... Right, so this is what I was talking about. You see how there's too much information here. If we do select and then we do ID, you see how there's this ID thing? If we do the expand property, you'll see that it gets rid of that and we just have the PID. That's what we were doing in that command. Copy this and then put it at the end of this. Okay, so now if we run it, we should see that it works. There we go. The first thing I want to do to actually dissect this program is we're going to find the main function. And luckily this still has all the symbols and stuff like that. We haven't stripped this. We can come into the modules list over here for symbols and then find our module, which is just the application. And these are all the symbols present within our program. We can find function names like main, printf, and then close handle, get last error, open process, all these functions that we use. So we're going to go into main, and by default, if x64 debug can, it will place a breakpoint into the main function, and so we don't have to worry about that. But we're in main now. Go into the graph view. It'll be a little bit easier to see by pressing G. Right, so we can see there's a compare being done to see if we supplied 2 arguments to the program. The first argument is always the application's name. The second one is PID. And so if it's not that, we'll see that it exits out with this usage message, right? Over here is where the magic actually happens. We can see our little call to open process here, but above it here are actually the arguments for open process. We'll take a little bit of a deep dive into this because it's really interesting to know. Okay, and you better be fucking excited. What we're going to discuss is the calling convention to understand why these arguments are appearing like this. So Windows uses the standard calling convention, and this is used by Win32 API functions. If we come into Visual Studio and actually hover over open process, we'll see the first thing that is shown to us is the type, or what this function returns, and then second we see the calling convention that this function uses. Open process uses standard call, as does the Windows API, so close handle also does standard call. Put is different, it uses that calling convention, right? Calling conventions basically tell you how arguments are going to be passed, and the naming conventions you'll see depending on the calling convention itself. We've seen cdec, we've seen standard call, and fast call is also present there too. But argument passing is the biggest noticeable thing. Since we're using standard call, we see that the argument passing order is from right to left. So what this means is that our open process function is going to pass in PID first because it's going from right to left. That's how it gets passed. It goes from PID to inherit handle to the desired access. The first argument that gets passed is the PID, and we'll set breakpoints on this to actually see that it is in fact the PID. PID goes in first, right? We see inherit handle placed here, and then lastly is the access that we want, and then we make the actual call. You can see these being passed in that manner. Now let's actually set breakpoints. We can press F2. Then we're going to place a breakpoint on each of these to really see like what these values are. Restart this and run. By default, it will place a breakpoint on the main CRT startup, which is fine. You can disable it, I'm pretty sure, if you don't like that, but go to run. We hit our first breakpoint. Whatever value is being placed at this area, we're going to move that into the lower region of the R8 register. The R8 register is a keyword size. We're moving it into the lower D word half of this R8 register, which is what the D over here means, the R8D, the lower D word. If we move past this instruction, so if we step a single instruction, we'll actually see that gets updated, right? And now this is in hex, but if we copy this value and we go to our programmer as calculator, paste it in decimal, this value is 31184, which if we remember is actually the process ID of the notepad process. So this checks out. We know that we've set the inherit handle flag to 0, and when you XOR something by itself, it's going to be 0. And if we move past this instruction, we'll see that yes, ECX, which will affect RDX because RDX just extended past EDX, becomes 0. This final value, this value of hex 1F, FF is being moved into ECX. This is actually our process all access thing here. We can see that comprised of all these different process access rights or whatever comes this value, which if we want, we can see all these different values it's comprised of, and add these values up, plus this, plus this. That's exactly the value we see inside of our debugger, and this is just what process all access is. And then there's finally that call into open process. So let's go into that actual call and see what happens. If we hover over it, you'll see that it goes into kernel32, the open process, right? This is what that call gets translated to. So if we double click this, we see we're currently in kernel32. Wait, inside of kernel32, it's not just calling, it's jumping to another place, which we already know is, there we go, kernel base. And once we're in kernel base, can just go into graph view. Oh, there we go. That's where the call happens. There's this instruction. So we can double click on this. And now what we have here, this is the NTAPI. This is the assembly stub that pretty much all the NTAPI that result in the syscall have. They all follow the same thing, which we'll see later. We'll dissect this structure and this assembly stub. Whenever we have an NTAPI function, it always starts with this line. The value of RCX is moved into R10 register. But then we get to this line, which is very important. If you think of NT open process having like a name tag or something like that, this is the ID value of that name tag. This is the number that belongs to it. These are called the syscall IDs, or the syscall numbers of these NTAPI functions. And we're not going to spend too much time here because we will go very in depth into this entire structure, this entire assembly stub when we talk about syscalls. At this line, a test is being done, and a test is just a bitwise AND operation in assembly. This address is very cool. This is just a k-user shared data structure, an offset of 308, which is just a syscall member of it. Don't worry if that doesn't make sense. We'll talk about it later. Depending on what we find here, a jump not equal instruction will be ushered out, and jump not equal acts depending on the value of the ZF flag. This is actually where that branching logic determines how we get into the kernel. Typically, we're going to be doing it through syscall, this instruction. Into-E was the legacy syscall instruction. This is how you would get into it on x86 systems back in the day, into-E. You might not be doing that much anymore. Typically, it's just going to be in syscall, and we can actually see how this works. Let's just set a breakpoint here by pressing F2. Let's restart this and run. Let's go past these. Okay, so we're here. This jump not equal, this will depend on the value of ZF. Right now it's 1, and this branched arrow is grayed out, meaning that this is not the path we're going to take because it's grayed out. We're going to land straight here. If we step forward a single instruction, we'll see that that's exactly what happens. That happens, and we step again, and the open process has been executed. Now if we go again, okay, we're at this place and we change this by double clicking it. Now we can see that this is red, meaning this is now the path that we're going to take. We're going to land in that legacy syscall instruction, the 2E interrupt. So if we step forward, our instruction pointer. It's currently on this line, and this is what we're at right now. I didn't mean to go on this much of a tangent, but I really enjoyed learning about this when I went into this blind. There's that. We have successfully dissected this program. We know exactly how this works. We are now ready to actually develop some shellcode injection implementations using one of these NTAPI functions. Nice. I just came back from the most life-altering walk I've ever taken. I'm pretty sure I just unclogged all my fucking chakras. And I apologize so much if you guys hear that annoying ass crackling sound. My microphone literally just shut the bed. And so for the next video, I'll try to get an upgrade. Sorry guys, genuinely. Okay, let's continue. Here's what I'll do. Since we can replace all these functions with their NTAPI counterparts, I'll just replace a couple of the functions instead of doing all of them, because I want you to go out after this video and try doing all of them by yourself. I'm just going to be doing the NT-create thread X, because in my opinion that's like one of the hardest ones to get going, or create process is also another one I've heard people having problems with. So I'll do NT-create thread X, I'll do NT-open process, as well as NT-close. You know, as your homework, you guys can go ahead and try to replace all the other functions to make a complete NTAPI implementation of a shellcode injector. Or you can also do DLL injection with this too. So here are the steps that you need to consider when using the NTAPI like this. Firstly, we want to set up the NT status codes that we're going to be working with. For us, this isn't that big of a deal. It's just one line, but it's important. Secondly, we want to create the function prototypes and define structures for the NTAPI functions that we're going to be using. We're going to get a handle on NTDLL. We go inside of NTDLL and find the actual addresses of the functions that we're going to be using. Now this can be done with getProc address. Remember, this is not done with OPSEC in mind, as I'm sure all the nerds among you already know that using getProc address or having that in your import address table or anything like that is already an indicator of compromise. But this is just basic theory and the very basics. Okay, so yeah, you can do this with getProc address. Step 5, after populating your function prototypes, the addresses of the NTAPI, just start building out your programs like you normally would. Step 6 is optional. You could set up some house cleaning to cleanly exit once you're done. Step 7 is just compile and enjoy. So let's start. What's rule 1 about? NT status? Well, you know how with functions like open process, virtual alloc, write process memory, or whatever, they all have their own return values or types. Well, that's not the case with the NTAPI. All the NTAPI functions return or are of the type NT status, which is a 32-bit or 4-byte value. So when you invoke an NTAPI function, like NTOpenProcess for example, it will return an NT status code depending on what happens. If everything went well, it will just return 0, as we'd expect. Any non-zero value that gets returned could warrant some investigation. There are a lot of these status codes defined, which we can see in a library like ntstatus.h, the ntstatus header file. Almost 30,000 motherfucking lines of just status codes for various different things. You can also find it on the docs, you can find it anywhere. Luckily for us, we only care if the function actually succeeded. So the NT-status code of success, or as it's called, status success, is just a value of 0. Error handling with this status code is very easy and straightforward because we can just evaluate what the function returns and see if the value returned was this status success value or not. Like here, you can see that we're seeing that if NTOpenProcess does not equal status success, then it will exit and it will show us the error code that it is. Now, see, the great thing is we get the error code or the return value built into this value, right? So we don't have to use getLastError anymore. We could just read the status itself because that's what's going to get returned. There are a bunch of different ways we can set up our status success value. I've never been let down by just statically hard coding and defining an actual value like this. We say, let the status success be this value. And it's just 0. The reason we've set it to 4 bytes long is because status codes are 32 bits or 4 bytes long. Yeah, but you can also use a success macro as well, like you can see shown here. In my header file, I'll just place this in somewhere with all my different printing macros that I use. Now, these are a godsend for me. I will always use them because I personally cannot just have a program not output information to me, which is why I'm a religious debugger when it comes to, printing lines and stuff like that. So yeah, I've just set up these macros. They're very straightforward. They allow for variadic arguments or whatever that word's called, so that you can supply different things like you would in printf, because it's essentially just printf. It is just printf. With this done, we can now move on to step 2, which is where we create the function prototypes for our NTAPI functions that we'll be using. Now, this is necessary because we can't just call the NTAPI functions and use them. They're undocumented, remember? So we need to craft a little skeleton so that once we get the addresses of these functions, we can just plump them into that skeleton or that You can think of it as like a house or something, so that prototypes come to life and we can use these functions. Now, you might be wondering how we're meant to do that. It's not like Microsoft's going to tell us how these functions are laid out or what arguments they take. Well, aside from like a few. Nope. But thankfully, our reverse engineering brothers and sisters have done a lot of the work for us. And there's a couple of ways we can get these function prototypes. First is by using the process hacker NT headers repository from the System Informer project. If you remember a couple of videos ago, I mentioned how I use process hacker for task management and process viewing. This is the successor to process hacker because process hacker isn't maintained anymore and now it's System Informer. Luckily for us, they have the function prototypes defined in this repository, and there's also this site that just provides a web GUI front to this repository and makes it easier to search for these functions and structures, so you can use this too. So let's search for the functions we want. NT-open-process, NT-create-thread-x, and NT-close. NT-close is the NTAPI equivalent to close handle. Okay, so once we find these, let's just pop them into our header file or somewhere in our project. It's a bit important that we set up the function prototype syntax properly. What you want to do is start the function prototype with type def, and then the type of the function, which as we know, since this is NTAPI, will just be of the type NT-status. And then add in this line, which just tells the function that it'll be using the standard call calling convention, because we can see that NTAPI expands to standard call. And finally, the name of the function. Now you might notice that there are some red underlined things in our arguments here. This is because these NTAPI functions require these structures in order for them to work. They're asking for them as arguments. And because we're dealing with this undocumented bullshit, we have to supply our own structures somehow. Luckily again, we can just search for these structures here, or we can use my personal favorite website, Virgilius. It's good if you can try to use the most recent dumped version that lines up with your current build and version of Windows. I'm currently on Windows 10 22H2. So we'll find our way to that section and then search for the structures that we need. Classically, you could also just dump your own structs so you know you're getting the latest ones. From the NT-open-process prototype, we see that it expects a pointer to the object attribute structure. We know that because it's standard to write p plus structure name to denote that it's indeed a pointer to said structure. And it also optionally takes in a pointer to the client ID structure. So let's find these and pop them down here in this header file. Remember that we need to add in the type def line before the structure and give this structure a name afterwards as well. And there we go. We can see that we got rid of a red line. Cool. Let's repeat this process for the client ID structure. With that done, we can move on to the other function, NT-create-thread-x. This one is asking for a pointer to user thread start routine as well as the PS attribute list structure. I'm actually going to change user thread start routine into pvoid here because this just lets us specify an address to start the routine from rather than doing it with that abysmal thing. And because our buffer from virtual alloc x is already going to be a pvoid, we can just apply it in here like this. This will work perfectly fine. Okay, so let's finally get the last structure, PS attribute list. Virgilius didn't have this one for my build, so I went back to the NT-doc site and got it from there. Remember guys, if one resource doesn't have something you're looking for, look around. This is a very important skill to hone. This dork-ass structure wants the PS attribute structure as one of its members too, so we have to include that as well. And you'll notice that with a large codebase like Windows, when you define these structures, and you aren't using a library that defines them for you, you'll be spending a lot of time going back and forth. Also, functions aren't the only thing that ask you to specify structures to them. Some structures ask for other structures as well. It's time for step 3. You need to get a handle on NTDLL. You actually already know how to do this, believe it or not. In the last Melda video, when we were doing DLL injection, we got a handle on kernel32 to look inside of it and find the load library function to get our target process to load our custom DLL. We're just going to be doing the exact same thing here with NTDLL, except instead of looking for load library, we're going to be looking inside of NTDLL for the addresses of the NTAPI functions we have built prototypes for, so that we can put them in there in their nice little cozy houses that we've built for them. I've made this function to sort of streamline this entire process. Pretty useful snippet to have, in my opinion. You can see that it just takes in one argument, which is just a module name that you want to handle on, and it's a wide char string, so make sure you use a text macro or just do an L prefix in front of the double quotes, and then we pass that module name that we supply into get module handle, and then it prints out some information about it. And it also comes with some, inbuilt error handling as well, which is really nice. and we can use it like this. If you want to find these functions, you can find it in my GitHub repository with the rest of this code. I'm sure these can be streamlined and made to be much more efficient, so you nerds can stop seething now. I'm working on it, you dorks. Slowly but surely we're getting better. Okay, let's continue. We have a handle to the NTDLL module. Let's now look inside of NTDLL and find the function names that we have here. This is what that would look like. We'll use the function prototype and define our own function name that will effectively now be the NTAPI function we're looking for. After this is done, what we have here is the NTOpenProcess function that's fully housed in its prototype that we've made for it. So we can now call this function like we would any other function, supply arguments, and it'll run. And we rinse and repeat this for the other functions that we have. Now we can start doing step 5. All we have to do now is, well, program this bitch out. Okay, so well, you know, there's really not much left for us to do here besides just populate those arguments for the functions that we now have access to, which is great because that means I don't have to spend a whole hour writing a whole new program. This is what we have so far. We have the getMod function, we have the PID, the R buffer, which is going to be the allocated buffer that we're going to place our shellcode in. This is the module to NTDLL, and these two are the handles to our processes and threads respectively, and then we have our shellcode here, and then the size of the shellcode. This is what our header file is looking like right now. We have our macros and our status success definition, we have our structures and our function prototypes. So it's looking very good. First thing we want to do is, after we've populated these, we're going to start with the execution and the injection. So let's just write that out. Yeah, so we can just call our NTOpenProcess function that we've named to ca-open because I'm unoriginal, and so let's do that. Remember, these return statuses, and we can initiate a status. Remember, it's NT-status. These return NT-statuses, so we'll name a variable called status, which is of the type NT-status, which we'll use to capture what these return. So there's that. For our first function, we'll do a look at that. Motherfucking IntelliSense or NTAPI, goddamn. So the first one, you guys have to be very careful. Okay, when I first started out doing this, I was making boneheaded mistakes like this. It says P handle, okay? It's not short for process handle. This means pointer to the goddamn handle. So don't try to put H process here, because it's not going to work. It's asking you to give a pointer to it, which we can do by putting this here. What we've done here is given it what it wants, a pointer to the process handle, and this is how it's going to give us that handle here. Next one is just the desired access mask. We already know what this is. We'll just do process all access. Sometimes if you're looking around on the internet, you might come across some implementations of this NTOpenProcess function where this argument right now is not going to be process all access. Instead, it's going to be the hex value that we came across before. It's the same thing. We've already covered this. For these two arguments, we know what these are because we had to go through that whole entire thing because of it. These are just structures. In the case of NTOpenProcess, it's actually the object attribute structure and the client ID structure. If we look at these structures, it's very easy to just use and set up, but we will have to initialize this structure. The first member is what we have to initialize, and it's just the size of this structure, which we'll do, and then the rest of it we can initialize it to null. And for this one, what we're going to do is initialize its first member, and that's going to hold the PID. So let's do that. The first one, member, is just going to be the size of it. And then I can just initialize the rest of those members. So if we do a comma, say, okay, just initialize the first member, then whatever comes after that, just set it to null or 0, whatever you want to do. There's another function, I'm pretty sure, that does this. I think it's like 0 memory or something like that. Don't quote me on that. I just seen it. There's other ways to do this. Let's put that here. Remember, it was a pointer to that structure that we've defined here. So it's going to be pointer to OA. And as you know, we can do that with this. So the next one is going to be the P client ID. So let's set that up as well. For this first member, the way that we're going to set it up is give the PID to this member. And there's many different ways to do this, but here's how I will do it. Look, you can do it like this, or you can do it like... You can do it like that, right? Or, you know, you can do it like this. Just have to make sure you cast it to the handle because it's going to be needed. Otherwise, it's not going to work with the permissions or whatever. The reason I'm showing you guys how many different ways to do this, and there's way more, I'm pretty sure, is because we often get really caught up in the literal syntax someone else uses instead of really trying to experiment and, you know, try it on our own, which is what we should be doing. Don't forget to experiment. Make sure you know, go wild, have fun with this. The way I like doing it is just like that. And once that's done, we now have this completely filled out and we will call it now. And what we can do is set up a check to see if what it returns is status success, to see if it worked or not. And if it didn't, we'll print out that error message. So let's try this. And because at this point we're not going to have a handle on this process or anything like that because it would have failed, we can just return exit instead of going to this label. Let me see, we're not doing get last error. Instead, we're just returning what the status value is, because that will be the error in itself, which I really, really like. I really think that's cool. It just doesn't make sense to go to a label here, because, you know, we don't have anything that really requires us to close it if it does fail. So let's just kill this program in this event. But, okay, now we can write over here, you know, if it didn't fail, let's print out that hprocess value. Let me just try to like run this real quick. So yeah, we've compiled this. Let's get a terminal in here and let's see what happens. I'm gonna try to do a process ID of 4 just because I want to see what the error is, and if that works, you know, then that's a really good sign. And if we can get a handle on a legitimate process that's not privileged, that would be really good too. So let's do 4 for the system process. This should give us an error access denied. Okay, so it did error out. So we can see that NT open process failed to get a handle on the process, and this is the error code. So this is the status code that was returned. Let's go look at what that value is. So let's control F here, and there we go. Yeah, so it's perfect. It's working perfectly well. Access denied. The process has requested to access an object but has not been granted those access rights. Perfect. So now let's open up a notepad and try the same thing. Oh my god. Look, it's worked perfectly. Look, we have a handle. Just ignore that we saw that. That was supposed to be the win API function. I'm so sorry. But you know, it's such a simple NTAPI function that literally we can do it right now. It will not matter. But yeah, all this takes is a handle. So it's literally the same thing as thing, but I just forgot to change it. I'm sorry. It's working perfectly well. Okay, this is really, really good. At this point, you would be trying to find the NTAPI equivalent of virtual alloc and write process memory to allocate a buffer and then write to the allocated buffer. But because I'm not going to do all that, and I'm going to leave something for you guys to actually go ahead and try and do, I'm just going to use virtual alloc and write process memory just as is. And we already know how to do that, so let me just skip over that real quick. Okay, I've added in some little comments to make it easier to separate. Over here, just same old, same old. We've been using virtual alloc a lot, so we should know what this does. Same with write process memory. Okay, this is just standard Win API. We allocate a RWX buffer with the size of our shellcode, and then we write our shellcode to that. So now, all that's left is for us to use nt create thread x, and then we'll wait for the thread to finish, and then once that's done, we'll close with the nt close function. So we're almost done. Let's program this out. Alright, so, well, we want a thread out of it, right? A handle to a thread, like we would with create remote thread or whatever. So this is also asking for a pointer to that so I can populate it. That's what we're gonna do. We want thread all access. You can supply that hex value here, or you can even put process all access here because it's all the same values. Let's just do thread all access stuff. This, it wants you to populate it with the pointer to the object attributes structure, and we've done that for open process as well, but just very easily do it here as well. And then it wants, remember, read it carefully, it's not asking for a pointer to the process handle this time, it's actually asking for the process handle this time, so let's just do hprocess. Now, pvoid start routine, we've changed this to what it was before. I'm just going to put our buffer here, right? This is just telling it, hey, where do you want to start from? Oh, start from the buffer that we created. So that's what that's doing. Now it's hard to see this one, so we'll go here. Argument, we're not going to supply it with an argument. If we were doing DLL injection, yeah, we would want to, because say you got a load library to be your shellcode in this case, your R buffer would just be saying, oh, load library. But load library requires an argument. So your next argument would be the name of your DLL or the path of it, if that makes sense. If that doesn't make sense to you, don't worry about it too much. I hope it makes sense to some people, but that's how that DLL thing was working. We're going to do null because it's an address, right? And then for these, all of these will just do 0. But the last one's going to be null again as well. We don't really care for any of these. That should be it. Let's do a little check just to make sure. And yeah, if at this point we would want to say, okay. Now over here, we could just do wait for single object. And we'll wait for it to finish infinitely. We'll wait because we're patient. And then once that's done, say start finished execution. And now we can replace these with, there we go. Yeah, this should be it. We should be good to go now. So let's run this. Okay, so if we run this, we should see a calculator spawn because we have calculator shellcode. So let's see if that works. Yes, let's go. Like, I knew this was gonna work, but I still, oh, man. Okay, yeah, so it works beautifully. And let me just show you a cool little trick for the people that stuck around this long. If you want to make all the kids at r/masterhacker really jealous, what you can do is actually print out the shellcode, like 1 byte at a time. Let's just do it right here with this. And here we go. Yo. I love this so much. But yeah, there we go, guys. You've done it. Seriously, you've done it, man. You've done it. Brr. With all of this done, you might now be wondering what the next step is in terms of getting lower and intimately closer to the CPU. Our next step would be to skip this NTDLL module and instead of calling the NTAPI directly, invoke those syscalls that we saw in those assembly stubs for these functions. Syscalls are our next step, and that's exactly what we're going to be covering in the next video. Once again, I'd like to extend a huge thank you to Maldev Academy for graciously sponsoring this video. I seriously recommend checking out their platform if you're interested in learning about malware development. There's so much information for you to absorb, and so much is constantly being added to the platform. Remember to check out the first link in the description or the pinned comment below for 10% off your order at checkout. With that being said, thank you for watching this video, and yeah, until next time, goodbye.